We're going to see more examples on higher order functions. Besides function as input, a higher order function actually outputs or manipulates other higher order functions too. Our example one was the integration using the sum. Let's look at the opposite problem of derivative. In mathematics, the derivative of g at x is equal to the gradient at gx, which is taken as gx plus dx minus gx divided by dx. So a derivation is actually a transformation of a function into another function. So we can have define derivation of a function g. It's taking a small difference dx equal to 0.00001 and return a function lambda x according to the definition. So the output of this function is another function. So derivative is also a higher order function. Let's take a look at derivative in action. We have from math package, we import sines and pi. This sines is from the package math. Derivative is our own routine. Our own cosine rather than the one from the math package can be taken as the derivative of sines. So cosine of pi over 4, which is 45 degree, is equal to 0.7071. Cosine pi over 2, which is cosine 90 degree, it's equal to this number. This number is actually close to 0, which is correct. If you have a cube, the derivation of x cubed is 3x squared. So 3x squared with x equal to 5 is 75. Our example 3 is the Newton's method. It uses the derivative in example 2. The Newton's method is to find the root of a function gx. That is, to find x such that gx equal to 0. Here is the method. If you have query on this method, you may check it out in the Wikipedia to know the detail. Here are the steps. You start with a guess x0 to be the root, assign it to x, then you check if the function is indeed close to 0. If it is so, you can stop and report the answer as x. Otherwise, you assign a new value to x by taking x minus away gx divided by derivative of g at x. Then you go back to step 3. So this is the loop that iterates until we have an answer. Here is the Python code. Define Newton's method for the function g given its first guess. We have dg equal to derive g. This is our example 2. Define new guess x. This routine will return a new guess as x minus gx divided by dgx, which is the derivative of g at x. And this is actually step 4. Define is close enough for a value v is to check whether the absolute value of v is close to 0. If it is, return true, otherwise return false. Then the main routine is define attempt with this guess. If it is close enough for the current guess, return the guess. Otherwise, return attempt with a new guess. So with all these sub-functions, we return attempt with the input first guess. Example 4. Computing square root using the Newton's method given in example 3. Square root of a number a is the number x such that x squared is equal to a. We can set up gx to be equal to x squared minus a and then use Newton's method to find the root of this guy, which is equal to 0, then which is the same as this equation. Here is how it looks like. Square is a function, input y, output y squared. Then square root of a number a is to return Newton's method by having the function gx equal to square x minus a and using half of a as the initial guess. So square root of 9 is about 3. Square root of 2 is about 1.414. In the last video, we have done the abstraction with the next term. For now, we can move on to abstract out the operator. We used to see just sum, and we can extend it to product, or rather a generic operator that is associative. Product is included. When an operator is associative, you can evaluate the operator in any order if they come one after another. Example 5. The fold function. It computes f0 all the way until fn for some function f by applying binary operator plus circle till fn. here it is define for operator function until n. If n equals 0, you return f0. Otherwise, you return the operator applying on the function and the for of f till n minus 1 under the operator. So here is f0, it's this, function fn is here, and the for of the front part is here, and then the operator here. Let's see the first use of for on exponent. We want to compute a to the power of n. So we have this, which is for op, f, n. So operator is actually multiplication. So we have operator is lambda xy, taking input x and y to output x times y. F0 is a, f1 is also a, the last one is fn minus 1 is also a. So f is lambda x output a, and n, as we saw, there are n here, there are n plus 1 here, therefore the last one should be n minus 1. So this n should be n minus 1. So when you look at it in the Python code, it looks like define exponent a raised to the power of n, it return for the operator is lambda xy, x star y, and then the function f is lambda x is a, and the n is n minus 1. Let's see a second example on the use of for. Here we are interested to find out the sum of digits in a given integer n. For example, when n is 3124, the answer is 10. 3 plus 1 plus 2 plus 4 is 10. So here is how we do it. Define sum of digits and return for lambda x comma y, x plus y. So this is op. Lambda k is the kth digit of the number n at k positions. So this is the function that we need to apply in the for. And count digits is the number of digits that we are adding. So we leave it to you to find out how to do kth digit and count digits. This should be easy. Let's see two more examples on for. We're interested in the products of digits for an integer n. So for example, n equal to 3124, the answer is 3 times 1 times 2 times 4, which gives 24. So this is similar to the one that we had before on sum of digits. So return for lambda x comma y colon x star y. This is multiplication now instead of addition for the operator. Lambda k, kth digit for the integer n at position k, and count digits n. So these two parts are both the same as before, except that in the case of sum it was a plus, now in the case of product this is a multiplication. Next, we want to do sum of square root of digits n. Example, n equal to 494, the answer is 2, square root of 4 is 2, square root of 9 is 3, square root of 4 is 2 again. So this is the answer is 7. So return for lambda x comma y colon x plus y. Again, this is a sum now. Lambda kth is the function f that we want to deal with, and this time the function f is to get the kth digit and then square root it. And we are doing this for count digits number of times. Let's finish up all about for. By now, you should realize we could discover more to be abstracted, as long as they can form patterns useful to many scenarios. Let's recap. Sum of integers can be expressed with higher order function, sum. Similarly, we would expect that the product of integers can be expressed in some higher order function called product. So what is this product? Product looks like this, similar to the sum, with a greater than b return 1 instead of 0, otherwise returns the term times rather than plus the rest. So this is product. Once again, sum and product are so similar. So we can take out the difference in the base case and the difference in the operator. Now we have for 2. If a greater than b, return the base. Otherwise, return the operations on term a and working on the for 2 of the rest of the terms. Then sum to be expressed in for 2 will look like this. Return for 2 lambda x comma y colon x plus y. So this is the operation, is the addition operation. The term is the same, the A is the same, the next is the same, the B is the same, and the base is 0. Whereas for product to be expressed in full 2, the operation is lambda xy, x times y, and the term is the same, A is the same, next is the same, B is the same, and the base is 1. In summary, we have Python functions are first-class objects. First-class means that they can be used for many purposes, such as to be named by variables, to be passed as an argument, or to be returned as the result. We have seen the power of higher-order functions. Each of these capture common programming patterns. Program can be very neat with the use of higher-order functions. We have seen sum as a higher-order function, taking in function, value, function, value to give value. We have seen product same as sum of the same types of input and output. You can try expressing factorial in terms of product and also can express exponent in terms of product. Full, assume we work from 0 to n plus 1 terms with the function to produce a function. For to allow operation from A to B on each of these terms and using this next function to produce another function. We also saw some higher order function, integral using sum, derivative, and Newton using the derivative. This was an old slide that we have the repeat pattern, which is also a higher order function. It outputs function. In that repeat pattern, we take in n number of times to repeat and the pattern to work on the picture, to produce a picture. Here's a homework that you can try. Instead of taking 3 parameters, you have only 2. Exclude the picture, repeat pattern to give you n pattern, which is a function instead of a picture. And then when you have this n pack as a function, taking in the picture, it produces a picture that is the same as this. And the two supposed to be equivalent. Now in this course, you are not needed to memorize the definition of sum, product, for, to, etc. What is required is to understand how to use higher order function to define specific functions and understand how to define higher order function by abstracting patterns. This course is not about memory work, but it's about understanding. And it is not about answers, but also about the process that you go through to learn.